about multi-agent emergence, and he's from DeepMind.
Cool, thank you. Yeah, Sherry asked me to give a talk on some of the multi-agent work that I did in the past, and I wanted to take this opportunity kind of like to do a retrospectively, maybe somewhat skeptical take on the subject and to reflect on what we've done, in particular in this multi-agent emergence, why it didn't take off, at least in the 2016 to 2019 time range when we were working on this, and what place, if any, does it have now. So first of all, just trying to define the terms, like when I say multi-agent emergence, really the picture I had in my mind in 2016 was something like this, where it's an environment in which multiple agents cooperate and compete, new skills or new capabilities potentially emerge out of the pressures that agents create for each other, and of course inspired by the growth of complexity that we see in evolution and natural ecosystems. So that's what I roughly mean by this. Oops. And so why and this is, I'll talk about some of the early work that we were doing way in the beginning at OpenAI, and in particular, why were we interested in multi-agent settings? One was that many applications, we believed, of AI were inherently social. Like agents that can use language are capable of social learning and teaching. Multiple AIs in terms of like robots or cars interacting with each other, safety and explainability. And so we thought, well, if we're going to put in this effort to build like an intelligence de novo, we should at least be bringing it up in social environments rather than bringing it up in isolation, so that it has like some social capability and awareness. The second reason why we were interested in multi-agent settings was that it was, to us, seen as a maybe hopefully a self-supervised path to intelligence. We'll use that term in quotes. Because I think right now, in hindsight in 2014, and this came up in the previous weeks of the workshop, kind of believe in this caricature that data plus compute equals, again, some kind of intelligence in quotes. And of course, there's a lot of dispute, but again, I think like that's a caricature that we have right now. But back in 2016, that was not what we necessarily believed. Like we also had this alternative hypothesis that maybe just a lot of compute plus some environment is going to be all that we would need for this, again, intelligence in quotes, or these capabilities. So we were at the time entertaining this hypothesis. And there were good reasons to believe that. We saw some work of Carl Sims on evolving virtual creatures. We saw how like a lot of compute spent on planning an AlphaGo managed to get really impressive results, or playing video games that beat human teams. And we also saw examples of this, these multi-agent competitive dynamics popping up in not even embodied algorithms. We saw like the advantages that adversarial interactions for generative modeling had. So we thought, okay, like there's maybe something big and deep there. So we wanted to explore this. And the way we've began exploring this, we've again like expanded that last equation a little bit. And we asked what would happen if you were to combine some multi-agent environment, simulated environment, some really, really simple objective, such as we picked hide and seek in particular, just some basic game, nothing too involved and complicated. You can explain it to anybody. And a lot of compute / reinforcement learning at really large scales. For the environment, just to give this, expand this example a little bit more, we were using some rudimentary physics simulation agents that can, say, move around in a 2D world, that can see each other, maybe sense some obstacles, or kind of like their relationship to other objects. They can grab and move some objects, so they can enact some persistent changes to the environment, and do other things like lock objects in place. So these last two things were basically just to see, yeah, can we, like, what can changing the environment get you, and like will we see some behaviors that try to go after changing the environment. Again, the reward was this team-based hide and seek reward. There are two teams. So what happened? What did we find? Well, we've ran the training, and in the very, very beginning, of course, we just got agents that moved around in this world randomly. And nobody was really winning at hide and seek. It was generally kind of random. Then pretty shortly, very, very shortly after running this training, maybe about 2 million or so episodes into the RL training, we saw some, I think, like predictable dynamics forming, such as like predator and prey, like chasing, agents were chasing each other. But again, nobody really kind of like developed some genius strategy. It was like generally pretty chaotic. Now, quite a bit later, well, not quite a bit later, but relatively, comparatively quite a bit later into the training, we first saw our, I think, like very, very interesting result that we were really, really excited about. That the team that is hiding, they learned to manipulate their environment. So basically bring up some boxes into the gaps, lock themselves in. So we thought, oh, agents are using tools, so great, or they invented tool use. So at that point, we did want to explore this a little bit further because, okay, we saw there's something interesting there. And so basically, or what we saw is not just tool use, but that the agents, like one team, like autonomously developed a counter strategy that was very, very successful in this environment. After about a similar amount of time, after about like 10 to 15 million, about 15 million episodes, we saw another team, the opposing team, actually developing the counter strategy to that. So this red team basically we gave them some ramps that they could use, that they could overcome the strategy devised by the blue team and still get in and like win at this hide and seek game. And here you can kind of see the win rates. They are jumping over the wall, yes, like above. So it's kind of like a ramp, and you launch yourself up and land, and you're in the protected room. But then what we ended up seeing, and then we kept on running it when we thought, okay, like this is going to be it. We can still publish a paper on this. Everything's great. But we kept on running it like for a couple of weeks more, just because we could. And we saw quite a bit later another strategy emerging in which these hiders, they took away the ramp, basically, and locked themselves in so that the tool created for the other team was not usable. So they developed, we saw at least like 3 stages of one strategy, then counter strategy, then counter strategy emerging out of this training and this environment. And it wasn't just in this room, and we also saw something, if we squint, we see some coordination emerging where like one agent is responsible for blocking the boxes, the other one is like responsible for getting the ramps, so that they are coordinating. And we saw this in fully randomized environments as well, not just in, say, that one room where first you have just this basic chasing, then you have more general kind of like shelter construction, where the agents, like we didn't necessarily like devise this particular arrangement of objects for them. Like they just took whatever they could get and locked themselves in here. And we saw similar ramp use also emerging for the opposing team in this randomized environment. We saw the ramp defense where the agents basically like move the ramps somewhere very, very far away in bad directions and lock them there so that they are effectively unusable, and the team kind of like still shelters themselves in to, again, protect from hide and seek. What we saw later was actually something that we didn't expect, which is the agents exploited the rules of this physical environment. They found that somehow if they land, and we coded up this physical simulation in such a way that if they somehow ended up on top of a box, they could exert forces on it. And so they ended up kind of like surfing the box around, effectively using it like a ramp, and still getting into the hiding place. And the last counter strategy that we saw towards this then is that the opposing team started locking. Okay, like we're gonna lock all of the boxes so that you can't use them. You can't do this box surfing trick, and that was as far as we got in this progression of skills. We kept on running it for longer. We thought something would come out, but kind of like after a couple of weeks, we stopped, and that's as far as we saw. So some surprising results, as I've mentioned, was this box surfing. We also saw some strategies where they just kind of like run away endlessly, and they get enough of a head start that then they just, are not, we had kind of like some limits on these rays, so they're still not seen. We saw some like some more physics exploitation where they just kind of like throw the box out of a ring through a weird physics glitch to also get rid of it, or some other type of like weird physics glitches where they do that. I didn't know Mujoko Physics Engine could do that, but apparently it could. Let's see. Should I mention? I'll briefly mention also one. Yeah, I'll mention it. Comparison to intrinsic motivation, like novelty seeking or empowerment, because it relates to, I think, like what Alice and I have been talking about over this past month, in that we try to compare the behaviors that you get out of at the end of multi-agent interaction to some of these novelty seeking methods. And we were finding that it really heavily depends on the types of observations that the agents receive, because if you handcraft the observations in just the right way, like, oh, I only pay attention to, or I only get to observe where the boxes are, or where the rays are, like you do end up doing kind of like sensible behaviors to find novelty in that space. But if you give complete observations that we gave to the agents that like include like distance to walls and so on, like way too many things are novel, and we don't really see anything interesting. So just briefly wanted to throw it out there just to tie it to what we're talking about. So then, this kind of like hide and seek, sure, it's nice, but like what can it be good for? And so we try to see if they are actually learning some,
Do you think that's because this space is too big, which is what Allison says? Do you think that's because the search space is too big, which is what Allison says is the problem?
I have a longer explanation for it. If I do you mind if I pass on it? Yeah, if that's okay. I think I put in like way too much into this talk, but let's see how it goes. Yeah, I want to address it later if that's okay. So we tried to also create some evaluation tasks that are like somewhat similar to what the agents were doing, like counting a bunch of objects, maybe locking a box and returning to it, and so on. Sort of like treating this as like animal intelligence tests or so on, and fine-tuning the agents to see if like do we get some agents that are able to then afterwards like they have learned a more general repertoire of skills that they're able to recruit for these tests. And disappointingly, the answer was no. Basically, it takes about the same amount of training, which is like for each of these like relatively in distribution tasks, it still takes about billions or millions of episodes, billions of samples to learn these. And having come with this multi-agent hide and seek experience really doesn't get you much. So that was then the thought was, okay, it's not just about this environment, multi-agent environment plus a lot of compute, because what's happening kind of like neurally in these networks is it doesn't seem like something good is being built up there, or something very reusable is being built up there. So that was our first disappointing result. But we're somewhat undeterred. We kind of like try to keep using this idea of environment, simple objective plus a lot of compute on our rail to try some other things. We got some like humanoid behaviors that looked weird, but I think were still interesting. We got some simple objectives like getting your collaborator into a goal, gave agents the ability to send some abstract communication symbols, and we saw some basic communication protocols emerge. They were compositional, so we got really excited because we thought, oh, agents create language out of necessity to accomplish goals. This is going to be great. We're going to like ignore all the warnings that Allison gave on Monday morning. We're going to learn these, like, say, some 100 basic words from operational experience. Then the other words of simple English, we will We didn't know how we would learn these words. Somehow, down the road, we would learn them. But that is not what happened. Where we don't have, we don't right now live in a world where we keep running these multi-agent environments, and they've invented music and they've invented Turing machines just to get better at hide and seek. This is not the 2024 we live in. So why didn't it take off? I don't think I have like super insightful or super unexpected reasons for this. And maybe this is something that we should have expected, like really should have foreseen in the beginning. But I think one big one is that the complexity of the behaviors seems to be bounded by the environment that we've pre-designed and the algorithms. So one particular nature of this environment is that lifetimes were still short and the world was not persistent. So you did some work to manipulate your environment, but really your world ended in about 60 seconds. So there was really not that much more need or not much more pressure to manipulate your world in some sophisticated ways because it got reset. And I would say this is not just kind of like for like a nature of like not us having enough compute. I think we simply don't have the algorithms as well for this. Like we don't have reinforcement learning methods that can do credit assignment over timelines of days or months. We have some things, but they generally tend to already work on some learned representations. But we want these algorithms to learn the representations to begin with. Of course, like related to this, there's no kind of like intergenerational transmission or cultural transmission effects that we could have here. Potentially, we've entertained that the physical world might be more appropriate because it has this complexity already. But at the amounts of like episodes and interactions that we were seeing in simulation, we would just not be able to do this many trials in the physical world to get these effects. The other reason that I think is a little bit more subtle is that tracking and projecting progress of this work has been really hard. So with LLMs, in hindsight, and kind of like what was getting developed at the time, was we have these scaling laws that tell us if you invest this much compute or you invest this much data, you will see steady progress. You don't need to think hard or do anything clever. You will see reduction in your perplexity. There might be kind of like some emergent effects, like suddenly it can do like long digit arithmetic, but those, you're not entirely relying on those. But for multi-agent, we have no such thing. All we have is really just this like spontaneous, erratic emergence coming out. So in particular with the hide and seek, you've had to wait, like nothing was happening, and then spontaneously, we kind of like had this surprising strategy emerge. And if we want to ask our society to make an investment, into like, okay, we want more compute and we want more like game designers to build these environments, and we're not going to be seeing any progress, but we promise like later on, like something really fun and something really cool is going to happen. Like that's going to be a tough sell. Whereas like with these scaling laws, you can say it's like, I give you compute, I give you data, you will see reduction in perplexity, which is like at least somewhat correlated to things that people who are giving you the resources are interested in. So I think that's kind of like another reason. And in general, I would say like related to this side by side, LLMs and then imitation learning and robotics were really making just much faster progress to this goal. So we didn't really push on this very much. I think at least like I personally didn't do much work on this after 2019. Yeah, relatively simple-ish transformer-based architecture. There was a policy. Given kind of like all the observations that I've mentioned, we had like lighter distances to other agents, but nothing more sophisticated than that. Just one relatively, for reinforcement learning standards at the time, relatively big transformer. There was long-term memory. But just long-term as far as like bounded by the episodes, like 60 seconds or 2 minutes or so. So maybe in this last part of the talk, and I still am somewhat working in this space, but in general, like have been trying to ask myself, what place does this multi-agent interaction, what place does it have now? Some kind of trends or developments that we've been seeing recently is that one place it has is kind of like work on simulated societies and potentially simulated social science, basically treating maybe like powered by LLMs. You would ask, okay, like what would a society or a group of LLMs do? What are some of the emergent social dynamics that happen there? Either like kind of like for fun experiments, or actually maybe trying to do kind of like a census on simulated humans, which there's a lot of potentially careful things there. The other place where I think we're starting to have multi-agent interaction now is in kind of like considering organizations of agents. So we saw these recent trends around spending more time on deliberation at inference time. So Noah talked about it with like chain of thought and like tree of thought and all of these various improvements. The other related development is that we're starting to kind of like build up agents that can try to solve some longer term tasks. So there's work on kind of like agents that do software engineering. There's work on kind of like doing enough prompting to get agents to solve like chemistry tasks. Antonio, in the first week of the workshop, talked about agents that can do interpretability research. So there is this like trend of using these models in the more agentic settings. And I think a lot of these agentic settings really are like the more natural takes on them maybe is inference time, like deliberation of a group. And a lot of these settings are done in a group, or potentially organizations of agents that solve tasks. Like there's like, you don't do things as a lone software engineer or a lone chemist. You have an organization of these. So I think one of the questions that I've recently been interested in is, do we see these types of wisdom of the crowd effects with large language models? And this is some of the work that we've recently been doing with actually with Antonio and some of the students at MIT. We've tried to look at debate as just kind of like as a first kind of like relatively minimal take on this, where we might have some example. I'm giving you like a math domain where it might start with a math question, and we have multiple agents trying to answer this math question. They might, they could be different models, but they could just be instances of the same model. And some of them might get this question correctly, some of them might get it wrong. And then what we do is we ask, kind of like do a second round, saying, okay, like using the solution from all of these other agents, copying the previous, what the other agents, what the independent instances have said, can you give maybe a critique of these answers and give an updated response? And so they, kind of like do something that sometimes superficially looks like reviewing and listening to what other agents. But I think in some of the examples we did see some genuinely interesting like critiques of the solutions that other agents have given. So I think like sometimes they were genuinely listening to what the other agents have said and updating the response back on that. And we do this for several rounds, and we arrive at a solution where both of the agents do give the correct response. And kind of like can see we've done it similar thing for chess moves as well, where again like they do give critiques like like this attack like leaves the bishop undefended or so, and so on. So we did see some of these critiques of what the other agents have said, and we do end up with better outcomes. And quantitatively, we do see an effect on a variety of kind of like contemporary benchmarks that this type of multi-agent debate. And I think like the exact nature of this debate, I think this is something that we've chosen just to like as the simplest thing that we can think of. But I think like the point is like trying to exploit the wisdom of the crowd effects in LLMs. Yeah.
How is chess move optimality higher than chess move validity? Seems like just deciding if a move is legal should be easier than.
Yeah. So that was. this was I'm trying to. I want to say, but I might be misremembering this incorrectly. That in this one, in the optimality condition, where actually this was relative, because we didn't. The optimality was, yeah, I remember. This was like an ELO, like a relative ranking, and it wasn't on the scale of accuracy. So this was on the scale of accuracy, because this was a binary question. This was at a different ranking where the debate was just like, the scale was set so that the debate was 100. And this, so yeah, I should say, like, this is the only one. I think like the rest are, I believe, are all accuracy in this one. Yeah. And we are seeing some things that more agents, more debate round seems to help, but I think informally we're not, again, like what's happening is like they're not, we haven't seen progress on them, like solving the Riemann hypothesis or something. So there is a plateau happening here, and I think like understanding why that plateau is happening, how we can improve, like how we can break it out of it. I think we, it's something we're looking into, but it's still, we're scratching our heads about. I don't think I'm gonna mention this. Yeah, so this general question right now, wisdom of the crowd effects, seems worth looking into. And overall, the talk, I guess this was multi-emergence. Why didn't it take off? I think environments were too simple, and it potentially expensive to design, more expensive than finding data or getting humans to rate binary things, and that the progress has been erratic rather than steady state. But as with all ideas, like they might go. Some ideas just might go through several seasons before they really pay off. And so I think it's still worth considering this idea. And then some thoughts for what place it has now is just in general for giving social competence to our AI models and social awareness and potentially organizations of AI agents. But I think it's still a tough question of, like, do we completely give up on these types of kind of like things emerge out of necessity and just like replace them with imitation and cultural learning? Or how do we maybe like reconcile the two and get the best of both worlds? I think is an interesting open question. That's my pick for what Shiri has asked. Yeah, that's it.
Thanks. So something that was pretty striking was that most of the examples you were showing in the first half of the talk with the sort of multi-agent environments were adversarial, right? There was a red team and a blue team, and all of the interesting behavior was getting generated from the fact that there was this sort of zero-sum game that they were trying to play. And all of the debate sort of LLM flavored examples in the second half are really cooperative tasks, even the debate ones, right? At the end of the day, everyone's kind of converging on the same answer, and there's no penalty for not doing that. There's no, sort of team one is setting problems that are so hard that team two can't solve them. Is there a path to getting some of those nice benefits from non-cooperative interactions into LLM training, or do you have a picture of what that might look like?
Yeah, that is, I mean, all throughout, we really wanted to somehow stress cooperation rather than competition. We really did not want to lean too heavily on competition, because, yeah, like, oh, should AI really be learning like from the very beginning how to compete with each other and outdo each other? It was a scary thought to us, but like empirically, that was like, I should say like the hide and seek is both cooperative and competitive, but you're right, there are not too many like the skills, the cooperative skills that are being learned are not very sophisticated there. Say with the emergent communication and emergent language, that was cooperative, and I think some interesting things happened there. But yeah, and I should also say, like, in addition, like there have been more competitive takes on debate, where you kind of like also have a judge, and the two teams are trying to debate and compete with each other to convince a judge. So that has been another take. And I personally like have been seeing competition more as like, I wish we didn't have to do this. But it seems like things are always like taking us to at least like have that as a factor. And I haven't personally, I have tried and I haven't found a way to get rid of it. I guess, Nick, you get to choose.
Hi, Dara, you Berkeley. So I think I'm over here.
Oh,
Yeah. Yeah. So I think so the debate examples that you showed. So I think correct me if I'm wrong, but I think that was in context, like no weight updating. And I'm wondering if you've considered actually using the like back and forth debate as a form of supervision in of itself as part of the like, fine tuning loop. Like I'm just kind of thinking like, for example, just seeing a trace of two humans going back and forth is kind of informative about the topic at hand, right? Because, maybe it means that it's contentious or you need to kind of tread carefully. Whereas if they reach consensus, it's trivial or something like that. So yeah, just kind of interested if you've thought about kind of integrating that as part of training at any point.
Yeah, so results of synthetic debates, we did not consider results of like humans debating a subject as training data, although there was one work from Anthropic that recently did look into it, and they claim they found improvement. Great. We did try to do it with synthetic data, and we do see improvement from fine-tuning agents, similar to kind of like the star idea that Noah talked about, where they fine-tune unsuccessful traces. We similarly fine-tune, and we actually have what we've been seeing personally is that when we just train on a single agent population, the fine-tuning seems to be harming. So we kind of like see this like self-improvement seems to degenerate. But with multi-agent, it seems like there's more variety in the answers that they're coming up or what have you. I don't feel very strongly about these results, however. It's just to say we did try it. It seems like it's helping, and multi-agent seems to be uniquely useful in this over single agent. I wanted to say something else about it, but it flew out of my head. I apologize.
Thank you.
So yeah, thank you. Wonderful talk, Lucy Cheek, Cambridge. So one of the things that looked really cool with some of the kind of early videos you were showing is that it looked like with the huntees that they were showing some kind of division of labor, like this, like I'm the guy that goes and gets the thing, and you're the guy that goes and does the other thing. Mm-hmm. And I wondered if one of the things that's well, firstly, that it feels like a kind of a cooperative thing, and that it's in the context of something competitive. But you can imagine a sort of survival-based game that stop your village from starving. That's got that element, but not the other. But I wondered if you had looked at the kind of combination of individual learning and multi-agent learning, where if you've got that division of labor, then you've got if the going and getting the ramp guy had been individually developing ramp fetching expertise until he was like the very best ramp fetcher that team could have had, and so on, whether or not you'd end up getting. Firstly, question is whether or not you kind of did those sorts of interactions, and secondly, whether or not do you think you'd end up getting more than the sum of its parts if you were to kind of mix and match that way.
Yeah, great question. So we did do it. There was another multi-agent environment and set of tests we've done I didn't show in this work. It was more like grid-based, larger, like thousands of agents doing things in kind of like 2D, kind of like gamey environment, getting resources and so on. We did see specialization coming out there in cooperative, but also competitive situations, where kind of like agents did seem to develop niches, and we didn't kind of like put that in, or so it seemed to be kind of like one consequence of doing this RL, where they all had separate policies. Did it come? So that was happening kind of like on its own. Did it lead to something that was more than the sum of its parts? We did not see that.
Okay, but there wasn't kind of individual learning in combination with that.
They were all policies that were learning individually, but they were always around in a joint environment. Yes, so we did not see. We did not.
Yeah, well, Lucy asked my question, but I could just follow up a little bit on it. That if you look, and I'm sure this is part of why Lucy thought about it. If you look at animal intelligence, even if you look at insects, it seems like one stratagem is this kind of developmental division of labor, but another stratagem is just division of labor in the community for something like ants. And I'm wondering, but you said you didn't. It would be interesting to see if you actually did assign a division of labor rather than waiting for it to emerge. Would you end up? Do you think you'd get better results?
It's hard to say because I think like the quality was still bottlenecked by the environment, by the complexity environment. So we saw that, some of them ended up, I guess like the niches were like they ended up foraging for some things, like for some kind of material, like the other ones were like figured out and knew where another type of material was, and they ended up foraging or doing something else with it. But we didn't try it in these types of like physically simulated environments where some unexpected things could really happen.
Right.
Just like in the simple 2D world, relatively expected things happen, and quantitatively we do much better.
So I was given a mic, so I guess that means I can still ask a question, or is the last question? Okay, so I'll let you undress there. Great. So so I've done a lot of stuff in this kind of wisdom with crowds, kind of generating things inside the context of LLMs, and I was interested. I kind of thought you were going to produce some kind of a different merger on the multi-agent environment with reinforcement, and this and this kind of just like emergent. I'm gonna prime a conversation of some kind with either fine tuning or context, or in our context, different subjectivities. But it seems like there's another potential pathway that I haven't seen really engaged, which is like, okay, well, let's say agents are engaged in persuasion, with one another. Then you can imagine kind of reinforcing complementarity in a way that's kind of like the reinforcement architecture of the first half, but lives in the kind of the cultural world model of the second half. So have you thought about kind of combining those architectures with a kind of reinforcement that's not RLHF, that's reinforcement effectively for complementarity, or reinforcement for some kind of collective outcome?
Yeah, I think it would make a lot of sense to do, and I personally don't know what the outcomes would be. We haven't had a chance yet, I think, like as a field, to see what the result of that will look like. Basically doing like long-term multi-turn RL on top of these big models is just technically like possible, but it's hard. But it makes a lot of sense to do that. So, but I don't think we kind of know yet what that would look like.
Great, thank you, Igor.